What are the different approaches in cross section balancing? We may do a volume balance, we may do an area balance, and we may do a line length balance. I will explain 3 of them. In fact, the volume balance some way I have already done when I was describing the product of stretches in 3 perpendicular directions when a cuboid is deformed to another cuboid or when an ellipsoid is deformed to another ellipsoid. There can be a more superior approach of mass balancing, because mass cannot be created or destroyed in the geological cases. However, the volume loss issue still persists. In the previous examples I have considered, the volume in the deformed material is same as the volume in the undeformed material, and using this principle the strain parameters were commented, but this is not always the case. Sometimes within our considered domain there is volume addition. Suppose there is igneous intrusion or volume subtraction. Suppose there is melting and that melt goes out of the system. In such cases the volume balance becomes problematic, and since there is a mass transfer, mass balance within the system is not working. No mass is destroyed, but within our system if some mass is going outside, some mass is coming inside, mass balancing becomes problematic. Is it possible to understand that there is a volume loss or volume gain? Pressure solution is one activity that can be picked up from thin sections and that can indicate the role of fluid. Fluid has come from outside. Then various growth structures can indicate addition of mass from outside. So, in such cases it becomes difficult to balance. If we can quantify the volume percent addition or removal, we might be able to do a better cross section balancing. So, here comes limitation. Material loss or gain needs separate study. Actually, it is not a problem of cross section balancing. In fact, it has a good prospect of raising more questions, doing more research and improving our ideas about the terrain. What are the other limitations? We almost always consider a single deformation that has produced a deformed feature, but this may not always be correct. There can be more than one deformation, but it is complicated and the geologist works out as a single deformation, and based on this idea we try to do a restoration, and this restoration can be wrong. The terrain which is very complicatedly deformed will be difficult to balance. It is coming from statement 1 itself, and statement 3 I have already explained. Regarding volume balance, I raise a question: what about the growth structures where volume addition happens? Growth fault is one of the well known growth structures. In coastal regions where there is an influx of sediment coming from the rivers such as the Indian east coast, it is possible to have differential compaction of sediments, and when the sediments are settling, that means when the volume is increasing, when the mass is increasing, syn deposition or faulting can take place. Syn deposition means during deposition. When deposition is happening, that time faulting starts and it produces Listric normal faults, and it produces this kind of reverse dragged structures within the hanging wall block, and is known as the rollover anticlines. The origin of growth fault is not very well understood, but it looks like in the hanging wall block there is more compaction. So, the sediments actually get compacted and a slip happens. These 2 points at one point were together, capital A and small a, capital B and small b, more compaction with respect to the foot wall block. Such growth faults, if someone is trying to do a volume balance, will be problematic. When faulting was happening, sedimentation was taking place. For other growth structures as well, the volume balance issue becomes problematic. Cross section balancing becomes difficult, but not impossible. Let us look at the area balance issue. The area balance can be applied if a section parallel to the principal movement direction is considered. We need to understand what is the meaning of the principal movement direction. Consider an oblique slip normal fault. In this case, these 2 points were together before faulting, and this defines a net slip. Net slip defines the principal movement direction for brittle faults. So, if I have a section of the rock, maybe river has cut a natural section, or for mining activity someone has made a vertical section and that is parallel to the trend of the net slip, then on that section doing cross section balancing is permitted. But consider in this case, if a geologist is picking up this vertical section or this vertical section, as per my drawing, these sections are not parallel to the net slip. So, any cross section balancing done on these sections will give wrong result, which means to do cross section balancing, to choose the proper section, one has to identify the net slip. For that, one needs to identify slick end sides on the fault plane. So, the pure geoscience knowledge is very much required. Under what situation this section can be used for cross section balancing? Let us make a simple sketch. Consider a deep slip normal fault. In this case, this is a net slip and these vertical sections are parallel to the trend of net slip. So, in this case, these vertical sections can be picked up for the cross section balancing purpose. If we choose an oblique section, what happens? Volume reduction or volume addition can happen and the area balance will not work readily. Now, this situation can happen in case of shale and salt diapirism. These are the 3-dimensional phenomena and the area balance may not work. Area balance may not work in case of bifurcating normal fault structures that undergo flow out of the plane of cross section. Let us make simple sketches and understand. In case of a mud diapirism or salt diapirism, what happens is that low density material moves up and the higher density material goes down. This produces round hinge fold, and if we are watching in the cross section within this geometry, continuously there is a volume change happening. Therefore, the volume balance or area balance from this curve will become problematic. In case of bifurcating normal faults such as this, if we are watching this cross section, not all flow happens within the cross section, there can be flow at an angle to the plane where I have drawn the diagram. So, these cases are to be avoided in straightway volume balance or the area balance. Let us look at the area balance method applied on a reverse fault and on a normal fault. This figure is that of a fault propagation fold, which I have already explained. The fault plane is shown by this green line. I am making it a bit bold. Now, I can choose a pin line here in the way that the pin line is perpendicular to the bedding plane and is loose line here. Since reverse faults are produced due to compression, this means if the pin line is static, I have to move the loose line here. This can be the initial position of the loose line and this is the final position of the loose line. Now, initiating the process, I can draw this line and one can calculate the area of this triangle. This area has to be equal to the area that has been lost over here. This area is the area gain due to deformation and here is the area loss. The area gain has to be equal to the area loss. So, the area gain measured over here is equal to area loss, and that area loss can be given by the length PQ multiplied by the length PR. The PQ length is known, area gain can be calculated. So, the PR can be obtained as area gain divided by the PQ length. Once the PR length is found, from this position that length has to be measured fix the point and draw the line. Once that is being drawn, we can restore the section in this way. So, this is the loose line and the different layers are brought horizontal, and we say that area balance has been done. The layers are now horizontal in an undeformed position, what is expected. The same principle will work if the geometry of the fault plane is a bit simplified, as in this diagram. Suppose this is the diagram. Why I am calling it a simplified diagram is that these sides are all parallel to each other, and one further point, actually this line and this line fall in the same line. So, here what we can do to restore the section, we can find out the area of the trapezoid and then the AT length. Suppose in my mental model this is the loose line, then this area of the trapezoid is the area gain and here is the area loss. Suppose this point is P, this is Q and here is R, then AT equal to PQ multiplied by PR. Therefore, the PR length is equal to AT area divided by the PQ length. Once PR is obtained, I can actually draw PR in the diagram and then say that, look, this was the original soft layer, and by deformation, by reverse faulting, it climbed up and produced this geometry, and now that this is a balanced cross section. So, here it was a triangular geometry and the trapezoid is demonstrated. What if some other geometry was produced? Since we dealt with a flat having a sharp contact with a ramp and the ramp having again a sharp contact with a flat, so this kind of kink fold was produced. Take this case of a flat and a ramp joined by smooth curve. We expect the fold to be produced like this if there is a reverse faulting. How to proceed in this case? And before that, what is the simplification in my diagram? This segment of the line, this segment, this line and this line are considered, this line is parallel to that line, this line is parallel to that line. Further, these two segments fall in the same line. Now, one can find out the area. We can create a mental model that this was the position of the loose line. Similar to this process, we are going to set P, Q and R, and we say that the area A is equal to PQ multiplied by PR. Therefore, PR is equal to area divided by PQ length. Once PR is obtained, we can actually move in this direction so many centimeter, drop a normal and say that this was the soft material before faulting. So, in case of a triangular geometry, in case of a trapezoid geometry, in case of this geometry, we are able to work out by the area balance method the restored cross section. Let us take the normal fault now. Such a normal fault, which is Lystric here, can be produced by several mechanisms. The mechanisms are stated here. There can be an opening and then this layer might get collapsed, produced due to antithetic simple shear. There can be other mechanisms possible. We just want to see from this cross section how balancing can be done. We have taken this simple case. Consider this situation or this situation. Here in my diagram, the simplifications are this segment of line is, this line is parallel to that line, this line is parallel to that line, and these two lines actually fall in the same line. Same thing here, this line is parallel to this line and this line is parallel to that line, and these two segments lie basically on the same straight line. First, find out the areas here. The geometry is irregular, it is neither triangular nor trapezoidal nor parallelogram geometry. Therefore, we have to apply our technique to find out the area of irregular geometries. We can drop normals on a straight line and these normals are equidistant. In the process described earlier, this area can be obtained. Consider here the loose line and consider here the pin line. Before deformation, this block was certainly here, and due to the Listric normal faulting, it has moved to that position. Simple logic says so. Same thing here. So, the loose line before deformation, say, was somewhere here, L initial, and this is L final. L final, let it be here. So, here the area opened up during deformation, or here the area opened up during deformation must be equal to this area defined by Li and Lf as the two margins of a rectangle. So, this area A found by this process is equal to PQ multiplied by PR. PQ, these are PQ and this is PR. PQ length can be obtained from the diagram, from the cross section that we are trying to balance. So, PQ is known, area A is known. From here we work out the PR length. Once PR length is found out, we actually draw this line and then we say that look, this is the restored block before deformation. Here this is the restored block, and during this Listric faulting, what happened? This PQ line shifted to this position. Here the PQ line shifted to this position. So, what is the basic difference between our exercise with normal fault and the reverse fault? The difference is the loose line L final and the loose line L final. From here, choice of L initial, loose line in the initial position, in the undeformed position, its determination is a little bit different in case of a reverse fault and in case of a normal fault. In case of a reverse fault, the L initial is found out in this place, and in case of a normal fault, the L initial is found out in this place. L initial is away from the fault, and in this case L initial is towards the fault, because in reverse faulting in compression, L initial is supposed to move to this position, and in an extensional tectonics, in case of normal fault, L initial is to move in that direction.